So far, I have introduced simple gates like a few single qubit gates like X, Y, Z and Hadamard gates, and also control X gates. And in this video, I would like to build on that and introduce more gates, specifically control Z and swap gates, which are two qubit gates, and also Toffoli gate, which is a three qubit gate. And we will also see some of their applications in building other logical structures. So let us start with the uh, control Z gate, which is also an entangling gate, as we will see in this video. So let me start by defining this gate. So suppose we use symbol CZ for this. So this gate acts almost like a control X gate, except that instead of X operation, when the control qubit is in one state, we would like to apply Z gate to the target qubit. So its truth table is this. Let's say this is the state of input qubits and this is the state of the qubits after output. So if the input is in 0 0, output is 0 0, 0 1, 0 1, 1 0, the output is still 1 0, because even though when control is 1, we apply Z gate to the target qubit, but Z gate does nothing to qubit in 0 state and gives a minus sign only when the qubit state is in 1. So 1 0 goes to 1 1 and 1 1 goes to minus 1 1. And in fact, I'm just using shorthand. These are all ket states like this. And as you can see that this is a symmetric gate, that we get a minus sign only when both qubits are in one state. And if otherwise, we always get a plus sign. So this gate actually is symmetric, and therefore you either represent it this way or this way. This is still the exactly the same gate. And that's actually the reason that in software this gate is represented by a symbol which is in fact look like a symmetric gate. All right, so this is the symbol of Z gate in many software like Qiskit. So from this truth table, we can write the outer product form of this control Z operator very easily, because ZZ state is going to 0 0 is going to 0 0. So 0 0 goes to 0 0. I can write it like this. Then 1 0 goes to 1 0. And 0 1 goes to 0 1. And 1 1 goes to 1 1. And from this, we can actually write its matrix form very easily, that only the diagonal entries are non-zero and all other entries are 0, because we see that there's no cross term appearing in the outer product form. All right, so let's see the action of control Z gates in some situation. We have already seen the action on the qubit states in computational basis. So let's take a little bit complicated example. So suppose I'm applying CZ as in 1 plus state. So it means that plus state is this. So let's express it. Even before applying, let me just combine all states 1 0 plus 1 1. Now when control Z applies here, we get 1 0 as it is, but the other state comes out with the minus sign. And now if I take 1 common from the left, I'm left with 0 minus 1 over square root 2, which we call minus state. So it means 1 plus state goes to 1 minus state. Okay, let's take another example. I'll get to swap kit in a little bit. So let's take another example that, let's say the control qubit is in plus state and so this is in one state. So before applying control Z, let me expand the state. So this is 0 1 plus 1 1. Now when the control Z is applied, this becomes 0 1 minus 1 1. And now if I take 1 common from the right, on the left I get 0 minus 1, which I can write minus 2. So now you see the plus 1 state has gone to minus 1 state. So I'm specifically showing this example to make sure that you all bear this thing in your mind, that controlling qubit doesn't mean that nothing happens to it. Even the state of the controlling qubit can change when it is in superposition state. Only when we are in the uh, uh, computational basis, uh, then this idea that control qubit is 0, something happens to the other one. If control qubit is 1, something happens to the other one. But in general, the states on both qubits can change after applying a control gate. Okay, so let's take another example. Let's say I apply control Z to plus plus state. So let's expand this state. So this becomes, actually let me just write in a single cut. I hope by now you get the idea that when it is written as 0 1, it actually means 0 cat 1 cat. Now when control Z is applied to this, nothing happens to this, nothing happens here, nothing happens here, but 1 1 state goes to minus 1 1. Now this is a state which I cannot write, as you can easily check, as a product of two individual qubit states. So it means that we started with a product state, that two qubits have a state which can be written as a product, but at the end we get a state which cannot be written as a product state. It means that control Z is indeed an entangling gate because it can produce entangled states. All right, so let's now discuss another two qubit gate, which is a simple gate. And even though it's a two qubit gate, it's not really an entangling gate. So it's called a swap gate with a symbol this, and usually we write it as swap. Okay, so we can construct its truth table like this. Let's say this is qubit q0, this is qubit q1. So let's say these are the states. So this q1 state goes there and q0 state comes here. So 0 0 goes to 0 1, 0 1 goes to 1 0, 1 0 goes to 0 1, 1 1 goes to 1 1. And if we want to write its operator form, I can write it from this truth table, because 0 0 is going to 0 0 plus 0 1 is going to 0 1 going to, sorry, this is 0 1, let me write 0 1. So 0 1 going to 1 0 and plus 0 1 going to 1 0 and 1 1 remaining as 1 1. And if you want to write its matrix form, this is the diagonal term 1, this is the diagonal term 1 here. Now this is the 0 1 0 1 1 0. So 0 1 1 0, and sorry, I made a mistake, so this should have been 1 0. So this left one indicates the row, so this is the second row. 0 1 0 1 0 1. This is the 0 1 0 0. This is the 0 1 0 1. This is the 0 1 1 0. This is the 0 1 1 1. Now this is in the third row because 1 0 comes in the third row. So this is 1 0 0 0, 1 0 0 1, 1 0 1 0, 1 0 1 1. So this is the matrix representation of this swap gate. Let's see its application in an example. So suppose I want to apply swap gate to this state plus minus, and let's expand the state. So this is, and write it in computational basis. So 0 0 plus 1 0 plus minus 0 1 minus 1 1. Now after applying swap, 0 0 becomes 0 0, 1 0 becomes 0 1, and 0 1 becomes 1 0, 1 1 remain as it is, and we can factorize the state again, and the minus comes here and plus comes here. Now you see the plus minus state has gone to minus plus, but it's not entangled. So swap gate, even though it sort of affects on these 2 qubit, is indeed a non-entangling gate. And there's another very important thing that we can note about this gate, that this gate can actually be implemented using 3 control X gates. Control X, control X, control X. Okay, and we can easily check. For example, it's 1 and 0 here, so this becomes 1 and 0 here, and this becomes 1 and 1 here, and then this becomes 1 and 0 here. And if we start with, let's say, 1 1 here, so this becomes 1 0, and this becomes 0 1, and this becomes 1 1. And similarly you can check for the other, and just like red state is going to red, and this light gray greenish blue is going to that the same color. So we can implement the swap gate using these 3 control X gates. Swap gate is sometime required when we have to change the order of the states. Let's now introduce another extremely important gate, and it's important because of 2 of its main applications that I will discuss both one by one. But before that, let's introduce its definition. This Toffoli gate has this symbol dot X, and it is actually sometime also called CCX or C square X, that there are 2 controlling qubit and then X gate. And its logic is just that its name. So if this is 1, this is 1, then whatever state is here, we get X gate applied. And if this is none of them is 1, nothing happens to this state. So X gate, this X gate is applied to this state only if both the control 1 and control 2 are 1 1. Otherwise this X gate is not applied. Okay, so this gate is actually important in 2 respects. One is that with this gate we can actually simulate all the classical logic. So Toffoli gate can simulate all classical binary logical circuit. And let's see how we can show that. If you recall, in classical binary logic, the NAND gate is universal. That if you can implement NAND gate, you can implement any logic. And NAND gate is essentially equal to an AND gate and a NOT gate. So a NOT gate is just an X gate, and AND gate has this logic that if both of the inputs are 1, then this is 1. Otherwise, if even one of them is 0, we get 0. And NAND gate is opposite, that if both of the input are 1, we get 0. If either one of them is 0 or both 0, we get 1. So let's see how Toffoli gate can simulate these gates. So in the Toffoli gate, suppose I fix this input state to 0 permanently, then and I make this as my output line. So now we can easily see that if this is 0 and this is 0, we get 0. If this is 1 and this is 0, we still get 0. And let me write it in this way. So if this is 0 and this is 0, we get 0. If this is 1 and this is 0, we still get 0, because both of the control has to be active before this X gate gets applied here. And if this is 0 and this is 1, we still get 0. And if this is 1 and this is 1, only then this 0 flips to 1. So it's mean that if you bind this input to 0 state permanently, then this Toffoli gate can implement an AND gate. Okay. And similarly, you can check that if instead of binding this to 0, if I had bound it to 1 state, then this would have acted as a NAND gate, because unless they're both 1, we would always be getting 1, 1, 1 here. And when this is 1, this is 1, this X gate would be active and the 1 would go to 0. And similarly, we can easily make the X gate out of it as well. You can fix these both of them to 1, then whatever input comes here, the X gate gets applied. So all the classical logic can be implemented using Toffoli gate. All right, so let's see another important thing that we can do with the Toffoli gate. We can construct higher qubit control X gates using Toffoli gate. Let me show how. So suppose you want to construct this gate that has 3 control qubit and 1 target qubit. Now I can do this using one ancilla qubit that is tied to 0 state, like this. So let's say I have a Toffoli gate applied to this ancilla qubit. So when both of these are 1, this 0 will be flipped to 1, and then I can have a Toffoli between these two applied here. And if this is 1, this is 1, and this is also 1, this 1 and this 1 will activate this gate, and our T will go to XT. And if one of these is 0, so let's say this is 0, then this 0 will remain 0 and this gate will not be active. And if this is 0, even if the both of these are 1, this Toffoli will not be active. And since this ancilla has been changed, we have to make sure that the ancilla is flipped back, because we might want to reuse this ancilla somewhere later on. So this the you can see we can just implement this 3 control circuit with only this structure, but we mostly add this part just to make sure that whatever state the circuit started in, the controlling qubits end up in the same state, because we might have to reuse these circuit to apply more iteration of this gate. And if we don't do this what we call an uncompute part, then this 0 will go to 1 and this will active, and then we won't be able to use this ancilla because this has gone into 1. And to apply this multi-qubit structure using these Toffoli gates, we have to make sure that ancilla, wherever it started, this ancilla qubit, means like additional qubit, it has to end up in the same state. So whatever we do in the compute part, we have to uncompute it to make sure that ancilla goes to the same state. So this way we can construct higher order controlling higher order or multi-qubit control X type circuits using Toffoli gate from this. And of course we have to have additional ancilla qubit. For example, if we want to construct a 10 controlling qubit, then we might need ancilla qubits of the order of 10. Okay, before closing this session, I want to talk about notation and an alternative sort of way of representing control gate. Suppose I want to implement this truth table, that when the control qubit in 0 state, I want the target to be flipped, and when control qubit is in 1 state, I don't want anything happen to the target. So I can do this with this circuit, because this X will flip these states. So for example, if this is 0 1, this 0 will make sure this becomes 1 and the control X gets active, and whatever psi is here, I'll get X psi here, and then this X will uncompute this X. So this is sort of the compute part, and this X will uncompute and make this 1 back to 0. And if this is 1, let's say this state is 1, then this X gate will take it to 0, and this control X will not be active, but this X will uncompute it and take it back to 1. So that I start with 1, I go to 1, I start with 0, I go to 0. So this type of circuit is actually very commonly needed. For example, sometime we need a control Z gate like this, or some control rotation, or some other controlled circuit where I want the control active on state 0 and not on 1. So in this case, people have introduced a special notation. So there is this open circle instead of a dot to represent this gate. So this gate is represented by this, where this now open circle mean in the controlling qubit that the control will be active when this control qubit is in 0 state. Similarly, for this we can use this circuit, and similarly for other control qubit multi-control circuit. For example, I can have, let's say, a multi-control circle. Let's say I'm talking about Toffoli. So this Toffoli can be equivalently represented as a circuit like this. So this means that this X gate will be active only when this qubit state is 0 and this qubit state is 1, then this will be active. Otherwise, this X will not act. For example, if this is 1 1, the X will not be active. If this is 1 0, the X will not be active. If it is 0 0, X will not be active. Only when the state on these control qubit is 0 and 1, this X gate will be applied. So wherever there is this O in the control on the control qubit, you should imagine that the controlling qubit has to be in 0 state instead of 1 state. With this, I would like to conclude this part, and just to summarize, we talked about control Z and the swap gate. Control Z flips the sign of the state when both qubits are in one state and does nothing otherwise. And because of this, it gives rise to entanglement. Swap gate simply swaps the states of two qubits, so it doesn't generate any entanglement. And then we saw that with Toffoli gate, we can also construct all classical logic because it can simulate universal classical gate. And we can also use it to construct higher order control circuits in quantum circuits. So with this, I would like to conclude my initial introduction to quantum computing, and from now on, we will start discussing simple algorithms to solve some simple problems.